So the brackets signify equilibrium concentrations. Okay, so if we go back to this problem, it says we have 1 mole of CO2, 3 moles of H2 placed in a 1 liter vessel. They react and come to equilibrium. At equilibrium, the H2O concentration is 0.387 moles per liter. And then what are concentration of CO, H2, and CH4 at equilibrium? So the brackets signify equilibrium concentration. Okay, so we are going to, in order to solve for equilibrium concentrations, we're going to use the approach called the ice table, where we have an initial concentration, that's the I, we have a change in concentration, that's the C, and then we have our equilibrium concentrations, that's the E. And so each one of those, ICE, that's going to be a line in this table that we're making. And our goal is often to find equilibrium concentrations or to find the equilibrium constant. Okay. So this problem is specifically looking for equilibrium concentrations. And we are given initial moles, but we are also given a volume. So we're given initial concentrations. We have 1 mole in a 1 liter vessel of carbon monoxide, 3 moles in a 1 liter vessel of hydrogen gas. And so we can start working through this to figure out equilibrium concentrations. Is everyone okay if I do this initial concentration is 1 mole per liter? Okay, you see we're in a 1 liter vessel. That changes sometimes, so keep an eye out on that. Our initial concentration of H2 is 3 moles per liter. And those are the only things that have been placed in the flask. So we don't have any products. So I like to just draw a line so I keep track of that. And I sort of make sure that I've checked for everything. Okay? So in terms of a change in concentration, we need to use the stoichiometry of the equation to determine how much change in that concentration there will be. For change, use the stoichiometry. Okay? So you've done this, whether you did it in an ice table or not. And we're going to have, if we say we are going to react some amount X of carbon monoxide, how many X is reacting of the hydrogen gas? 3X, yeah, so we're using that stoichiometric coefficient. So I'm using a minus sign to represent the fact that that reactant is reacting away, it's going away, the concentration is decreasing. So we have one, let's see. Okay, yes. And then when we form products, we're going to again use the stoichiometry. So we have plus some amount X for the methane and plus X for H2O. Again, stoichiometric coefficients of 1. All right. Make sense? Questions? Okay, so then at equilibrium, here I like to draw a line to remind myself that I'm going to be doing some math in a column. So at equilibrium, our concentration of CO is 1 minus X moles per liter. I'm going to leave off my unit for now. For H2, I'm going to have 3 minus 3X. For methane, I'm going to have X moles per liter, and the same for H2O for water. Oh, okay. we're given one other thing in the problem, right? So we know that the concentration of water at equilibrium is 0.387 moles per liter. So that tells us that X must be equal to 0.387 moles per liter. So based on that, we can now solve for every other equilibrium concentrations because we know that the concentration of CO is 1 minus X, H2 is 3 minus 3X, and CH4 concentration is X. So this is equal to our concentration of H2O. The concentration of methane, CH4, is 0.387 moles per liter. The concentration of H2 is 3.00 minus 3 times 0.387. What does that give us? 1.839 moles per liter. And then for carbon monoxide, 1 minus X, 1 minus 0.387. We get 0.613 moles per liter. Okay, so we've answered the question, the problem, which was to solve for the equilibrium concentrations of each of those reactants and products in the equilibrium. Questions on that problem? All right, so if we ask you to solve for K, yeah. No, so you can do this for gases and things that are aqueous. So so let's say that water was listed, that's not a great example. If one of these things was listed as aqueous, then you could still include it the same way you would. You can have mixes of gases and aqueous species and solve everything the same way. Really, the only difference comes in is if you have a solid or a liquid, and you just don't include those in any of the equilibrium things. So if we had a solid listed here, we wouldn't even bother filling out that column. Yeah. Okay, so if we solve for K, we're going to do this the same way as we had done before. We're interested in our CH4 concentration times H2O divided by the concentration of CO times H2 cubed. And we're going to plug in the equilibrium concentrations. I'm going to leave it like that. And when I solve this, I get a value of 0.0393. Again, don't worry about units on K. Is that reactant favored or product favored? Reactant favored, yes. Value of K is less than 1, so it will be reactant favored. Make sense? Slide. We ended up with we were supposed to solve these 4 things. Cool. I want to do one more example because there's something nice that happens mathematically in this problem, and I want to make sure you're all aware of it. So here we have a reaction of NO gas in equilibrium with N2 and O2. We're given the equilibrium constant for this reaction. It's 2.4 times 10 to the third. We have a 1 liter flask, and we put in 0.6 moles of NO. And we want to find the equilibrium concentrations. So we have an initial concentration of NO of 0.600 moles per liter. Again, we're given moles, it's in a 1 liter flask. And no initial concentrations of our products. So we're going to have minus 2x for the concentration of NO, stoichiometric coefficient of 2, x and x for N2 and O2. And then at equilibrium, we're going to have 0.6 minus 2x for the concentration of NO, x moles per liter for N2, and x moles per liter for O2. So we aren't given any equilibrium concentrations, right? So now we have to mathematically solve for x. We're given the equilibrium constant k. It's 2.4 times 10 to the third. So it's going to be reactant favored or product favored? Product favored, it's a large value of k. We have x times x for our products. And we have 0.6 minus 2x for our reactant. And don't forget to square that, okay? There's our KEQ, our K. Again, this is concentration of product N2 times O2 over the concentration of NO. And you have to square that. It's easy to forget that square, okay, for sure. So watch that. All right, so how do you solve that? Plug it in your calculator, right? There is an easy trick for this, but and you see this occasionally. If I write out the problem like this, does anyone see what this is? If I write it out like that, we have in our fraction, we have something squared over something squared. So we have a perfect square. So if we take the square root of both sides of this equation, we can solve for this much more easily than if we were to solve the quadratic. Okay? So if you get to the point where you think you have to solve the quadratic, take a look. There might be some mathematical thing that you can do to avoid that. We very rarely have to solve the quadratic in this class. All right, so square root, square root. In fact, I don't know that we ever really will. I'm going to show you one example later on when we do, but so now we have the square root of 2.4 times 10 to the third equals x over 0.6 minus 2x. Much easier to solve, right? Questions on that? And while we're doing it, might as well give you the answer for x. That way you can try it out. Make sure you can get this, okay? Make sure you can then solve for your equilibrium concentrations. Yeah, question? The last slide? On the questions before you all have a great weekend? All right, everyone, enjoy the weather.
I was just like confused.
Yeah.
And I also emailed and I CC'd you. So thank you.
Yep, absolutely. Okay, so, good. How are you? Good.
Have a good weekend, Dr. Fair.
Oh, yeah, okay, thank you. Yep.
Yeah, I recently, like, I was in like some Tuesday exams really difficult. They recently emailed me back.
Don't tell me they want you to take it tonight and they know it's open morning.
Yeah.
You serious?
Yeah, so they recently emailed me, we understand that you could not take your exam or rescheduling until Monday or Tuesday. On further discussion, the department policy said that you may take the negative exam in today's session. It starts at 5:30 today. So basically now they're saying I can, it says urgent makeup exam today. So now they're saying I can't today. I don't have a fully charged iPad. I don't have my iPad fixed because I have work today because like I told my work that, hey, I got denied, I can come in today, and so now I'm like, because they, like, I can't keep jumping. If I'd known yesterday, if you told me yesterday I could take it today, I'd be ready today. But I'm just now saying this. I was looking at me.
I'm so sorry.
No, it's fine. It's just.
Thank you for telling me, and I will definitely bring this up in a meeting, because that's not an issue.
Yeah.
You can't beat it.
Because now upon further discussion that I can, like.
Right.
What made it the first time I got denied?
Right.
Like, that's why I was just like, I'll forward this to you, but
Yeah,
it was
me
just
too.
annoying because now I have to wait.
Me too.
Now I for sure have to wait until the end of the year, when I could have taken it today if I just.
I think you maybe should respond nicely, but say those things.
Yeah.
And I mean, yeah, I'd be pissed if I were you.
Yeah, I mean, I'm not like, I'm not like stressed about it, like, oh no, I can't take the exam, like, it's gonna be fine, I can take it in
Yeah.
December, oh well.
Yeah.
But the fact is, like, if I could've got it out of the way, but now knowing as of today to take an exam, like this morning, and I'm just now saying it, and they told me to respond, so there shouldn't be any penalty, cause, right?
I wouldn't think so. I mean, yeah, respond and say.
It says you only need to respond if you cannot attend tonight's exam, and I'm just now seeing this, and the
Right.
exam's in 3 hours.
Yeah, I mean, I think you need to say that. I just saw
Yeah.
this email. I had already done this because I was denied initially. You know, had I known, even yesterday, I would have probably been able to do it, but
Yeah, just.
I think
It's just like instantly, and I'm like, oh, well, I can't just take back, I literally just told my work, I can't take back everything I just said to them, and vice versa, go
Right.
back and forth.
No, you can't do that. That's not.
So,
fair.
but yeah, I just wanna make sure prior, that there wouldn't be no like penalty for it if I couldn't, like, cause it said just only respond if you can, so.
Yeah, I can't imagine there would be a penalty. And my God, if there was, people will deal with my wrath.
So thank you so much, I appreciate it.
Have a great
Yeah,
day.
you too, have a good weekend.
You too.
I think I've got this question on the homework. It says
Uh-huh.
that equilibrium can be established when 0.25 mole factor 2 is placed in a 1 meter container, so why is that?
Because you only have one of the reactants. If you had both of the reactants, then you could do it.
Okay.
The volume, the mass, the moles doesn't matter.
Okay, so if both of them were in there.
If
I
both of
think
them were
another
in there.
option was I think they added more of a product in there, so
Yes.
since there's only one product, that's okay, right?
Correct.
Okay.
Yes, and if you have one reactant and one product,
Mhm.
then you can also get to equilibrium under some conditions. Unless something with K being, I saw this problem earlier. I think if K was like, the ratios of K were such that,
Like, the product was favored?
yeah, or
Okay.
something like that, yeah.
Okay.
Yes, if it was product favored, yeah.
Okay.
Like heavily product favored. Oh my God.
Alright, have a good weekend.
You
Dr.
too, enjoy.